So today's topic is implicit differentiation. Now, what we are talking about when we say implicit definition is there is a difference between an explicit equation and an implicit equation. All of the equations that we have dealt with have been explicit equations. What an explicit equation is, it tells you y equals something or x equals something. Okay? So most of the functions we have dealt with in this class is it has y, it's solving for y explicitly. Most equations we see in math are solved for y explicitly. Like an equation of a line is solved for y explicitly. An equation for a parabola is solved for y explicitly. But we know there are equations out there that are not solved for y explicitly, and you know those equations. The most famous one, or the one that you probably are most familiar with, is the equation of a circle centered at 0, 0, right? This is not solved for y explicitly, but you know this forms a circle centered at 0, 0. So how do we differentiate something like this? And that's what we're going to be doing today. So we want to consider functions of the type x squared minus 2y to the third plus 4y is equal to 2. This equation would be really challenging to solve for y. Thus, we have to introduce a new method to differentiate these types of functions. This method is called implicit differentiation. Now, before we move on, if I have an equation like xy is equal to 8, you could just divide both sides by x, and you would get y is equal to 8 over x. And then you could use the quotient rule to differentiate this. Or you could change this into and just differentiate this. This is much easier. However, try solving for y here. You really can't. You could move the x squared to the other side, and then you could factor out a y, but then you'll have a y on the outside and a y on the inside, so it'd be really challenging to solve for y here. So that's why we need to develop a new method to do differentiation for an equation that has a bunch of x's and y's together, and you can't really isolate the y. Okay, so here are some things to consider when we are doing implicit differentiation. Even though we have two variables, differentiation is always taking place with respect to x, not respect to y, with respect to x. If a term only has the terms involving x alone, just differentiate like you normally would. There's no change there. However, if there are terms involving y, you have to apply the chain rule. So take the normal like power rule or whatever, but then you have to apply the chain rule because y is defined as a differentiable function of x. And we'll talk about this a little more. So here's actually the big thing here. If I take the derivative of x, that's just normally 1, right? We all know that. But if we take the derivative of y, we can't just say that's 1 as well. Because in these equations, y is a function of, it's defined implicitly as a function of x. So when you take the derivative of y, you don't put 1, you put dy dx, since we're taking the derivative with respect to x, not for y. Or using prime notation, y prime. I don't know why I didn't put that there. Now, here is how to do implicit differentiation. You differentiate both sides of the equation with respect to x. Obey the chain rule by multiplying by dy dx every time you differentiate an expression containing y. So anytime you have a y term, you take the derivative using the power rule, the quotient rule, whatever, but in the end, after, you have to put dy dx, because we're not differentiating in terms of y, we're differentiating in terms of x. The next step is any term with dy dx, we all bring those terms to one side and all other terms on the other side. And then we solve for dy dx. Usually we would have to factor out a dy dx. That's a lot of stuff going on here. So let's actually find out how to do this. So I see an equation here and we have to differentiate it. I can't really, this is actually the one that I showed you earlier. And there's a bunch of x's and a bunch of y's. And we're kind of stuck here because we can't solve for y. So here's how to do the differentiation of this type of equation. So I'm going to differentiate. Actually, I'm going to rewrite this whole thing here. So I'm going to differentiate both sides. This first term has an x term only. It has an x. There's no y here. So this is normal differentiation. This is just 2x. Now here, if I differentiate, it's a y term. So this is what happens when you have a y term. I do the normal power rule like I normally do. Minus 6y squared. But then since y in itself is a function of x, I have to take the chain rule here. And the derivative of y with respect to x is just dy dx. So anytime you have a term with y in it, you do normal differentiation, but then you have to chain dy dx. Because y is a function of x and we're differentiating in terms of x. Plus, remember that if the derivative of 4x is 4, the derivative of 4y is 4 as well, but then you have to chain because it's y term, it's a y term. So I do dy dx, and the derivative of 2 is 0. So I did step 1. Step 2, I'm going to isolate dy dx by getting all of the dy dx terms on one side and anything without a dy dx on the other side. So these terms have a dy dx. I'm going to keep them on this side. I'm going to bring the 2x to this side. So I have minus 6y squared dy dx plus 4 dy dx is equal to negative 2x. Now I need to solve for dy dx. So there's one here, there's one here. What I'm going to do is I'm just going to factor it. And so I'm left with minus 6y squared plus 4. And then now I just need to get dy dx by itself. So I'm going to divide both sides by negative 6y squared plus 4. And so my derivative is this. You don't even need the parentheses here. Okay. This just takes practice to get used to it. But remember, what we're doing is we're finding the derivative of the equation with respect to x. So when we see a y, we're not taking the derivative with respect to y. Since y in itself is a function of x, we need to do the chain to get dy dx. So let's look at example number 1 here. Find dy dx for x, y plus y is equal to 8 at 3, 2. So here, they actually want us to figure this out at 3, 2. So first step is we are going to go ahead and take the derivative. Now we have to be careful here, because if you see here, we have to apply the product rule. I have x times y. And so I know I have to do the product rule. First times derivative of the second. So it's the first, which is x, times the derivative of y. The derivative of y is dy dx. Plus the second function times the derivative of the first, which is the derivative of x is just 1, plus the derivative of y, and the derivative of 8 is 0. So once again, I see x times y, so I have to do the product rule. First times derivative of the second, x, the derivative of y is dy dx, plus the second, which is y, times the derivative of x, which is just 1, plus the derivative of y, it's dy dx, is equal to 0. Now next thing, anything without a dy dx, I bring to the other side. So this is just a y by itself. That's going to go here. And then I'm going to factor out a dy dx here. And so I'm left with x plus 1. And then I divide both sides by x plus 1. And so my derivative is negative y over x plus 1. So if I want to find the value of the derivative, I just plug in my x and my y. So here they can't just give you an x if it's an implicit differentiation, because our equation will usually come with x's and y's. So they give us the point 3, 2. We plug in 3 for x, y for 2. So dy dx at 3, 2. So this is the notation for the derivative at 3, 2. And so we just plug in those numbers in. That's equal to negative 2 over 3 plus 1. And that's equal to negative 2 over 4, which is negative 1/2. Okay, if you think you know what's going on, maybe try example 2 on your own. If you don't know what's going on, just go ahead and follow along and then try maybe the next example on your own. So you want to try it on your own, pause the video. So the derivative of x is just 1. I have 3xy, so I know I have to use the product rule. So the first function is 3x, the second function is y. So the first times the derivative of the second. So the first function is 3x. The derivative of y is dy dx. Plus the second function, which is y, times the derivative of the first function. The derivative of 3x is 3. And then I'm going to take the derivative of minus 2y squared. That's minus 4y. But since this is we're taking the derivative with respect to x here, I have to put dy dx when I see a y term. And then here the derivative of 2 is 0. So once again, what I'm going to do is I'm going to bring the terms without a dy dx to the right side. And what I'm going to do is I'm going to, actually, I'll do one more. So then 1 goes to the other side, and the 3y goes to the other side. So this term and this term go to the right side since they do not have a dy dx. So this is going to be equal to -1 minus 3y. And then I factor out a dy dx. To save space, you could have just done the moving and the factoring all in one step, so you don't have to break up into 2 steps here. But I'm breaking it up into 2 steps. So I factor out the dy dx, and I get 3x minus 4y. And now I just solve for dy dx. So dy over dx is equal to -1 minus 3y over 3x minus 4y. By the way, you might see this on a multiple choice test. They could write this as 1 plus 3y over 4y minus 3x. They could have multiplied the top and bottom by -1, right? I just want to make sure that you're able to see alternate forms of an answer. Now, if I want to find the derivative at 1, 1, this is going to be equal to -1 minus 3 times 1 over 3 times 1 minus 4 times 1. And that's -4 over -1, which equals 4. Okay, let's move to example 3. Example 3, I actually think you should be able to do this one. This one, you don't need to plug something in at the end. I just want you to find the general derivative function here. So you could pause the video. I really suggest that you try this one on your own. This one isn't too bad. So if we take the derivative here, the derivative of y cubed is 3y squared. And then since this is a y term, I need to put dy dx plus 2 times 5 is 10y. That's the derivative here. But since I'm taking the derivative with respect to y, I need to put a dy dx. the derivative of minus 5y is minus 5, but since this is a term with a y, I need to put dy dx. Minus x squared is just minus 2x. There's no y term, so it's just normal. And the derivative of negative 4 is 0. So what I'm going to do is I'm going to move the negative 2x to the other side, and I'm going to factor out a dy dx. So the steps that I would do, you see here, I would move this to the other side, and then I would factor, move this to the other side and factor. I'm just going to combine that all in one step to save space. I'm going to factor the dy dx out of these three terms and move the 2x to the other side all in one line. So I get dy dx 3y squared plus 10y minus 5 is equal to 2x. So I brought the minus 2x to the other side, and with the terms that I have left, I factor out a dy dx. So I know I'm going to divide both sides by this, by the 3y squared plus 10y minus 5. So that must mean that dy dx is equal to 2x over 3y squared plus 10y minus 5. So remember, what I did here is I just divided both sides by this to get the dy dx by itself. But I don't really need to show that step. In like the AP test for the free response, you don't need to show those little algebra steps. Okay, they assume you know how to do algebra. Okay, example 4. I actually want to show you that you do not need to do implicit differentiation here. But I want to show you that implicit differentiation and regular differentiation gets you the same thing. Why do you not need to do it here? You could easily solve for y here. All the other ones we've done, you can't solve for y. You can't really solve for y here. So let's do this implicitly first. So my implicit. So if I take the derivative of y e to the x, this is the product rule. So it's first times derivative of the second. And remember, the derivative of e to the x is just e to the x, plus the second function, which is e to the x, times the derivative of the first. The derivative of y is dy dx. And then the derivative of 3 pi, remember pi is just a number, so this is 0. Now this becomes really easy to solve. The dy dx is here, so I need to bring this to the other side. So I get e to the x dy over dx is equal to negative y e to the x. So if I divide both, I need to get dy dx by itself. So if I divide both sides by e to the x, that cancels here and that cancels here. So dy over dx is equal to negative y. Now, I'm going to show you that you could do this one without implicit differentiation, and you get the same answer. So what we're going to do here is we're going to solve explicit. We're going to solve for y explicitly by dividing both sides by 3x. And so I get y is equal to 3 pi over e to the x. Right, everyone see what I did? I divided both sides by e to the x, so I get 3 pi over e to the x. And now I'm just going to differentiate y. So y prime is equal to bottom times the derivative of the top. So I'm using quotient rule here. So the bottom times the derivative of the top is 0 minus the top times the derivative of the bottom. So the top is 3 pi. The derivative of e to the x is e to the x all over the bottom squared. So if I square e to the x, it's e to the 2x. This becomes 0, and I get y prime is equal to negative 3 pi e to the x over e to the 2x. I have 1 e to the x here, and I have e to the 2x here. So what I can do is I can cross this one out, and I'm just left with an e to the x on the bottom. So I get y prime is equal to negative 3 pi over e to the x. And guess what? These are the same things. Because see how this is negative y? What is y equal to? It's 3 pi over e to the x. And so negative this is negative 3 pi over e to the x. So you see what we're doing when we're doing implicit differentiation is whenever you see a y, what it really is, it's a function of x. That's why when we take the derivative of y in an implicit differentiation rules, we do the dy dx because y is really a function of x. It's just that for some of these questions, we can't really figure out what that is. But y really is a function of x. And so that's why we have to put dy dx when we derive differentiation implicitly. Okay, so let's look at example number 5 and see how this one would work with the trig function. It's basically the same thing here. Okay. So we're going to differentiate both sides. I know that the derivative of cosine is negative sine. But remember, it's not just an x on the inside. So that means we have to do a chain rule here. So if I'm going to do a chain rule on the inside, I see I have x times y. So that means I have to do product rule. So first times derivative of the second is x times dy dx, because the derivative of y is dy dx, plus the second, which is y, times the derivative of x, which is just 1. So I'm just going to leave that as y. And then I take the derivative of the right side. That's equal to 1 plus 3 dy dx, because I have a y term there. So what did I do? I took the derivative of the left side. Derivative of cosine is negative sine. So I do negative sine xy. But because this is not just x by itself, I have to do chain rule. But this is a multiplication. So my chain is actually a product rule. Okay? And that's where this x dy dx plus y comes from. Okay, so I want all the terms with dy dx on one side and the terms without dy dx on the other side. So what I'm going to do is I'm actually going to distribute negative sine xy into both of these terms. And so I get x times negative sine xy is minus x sine xy dy dx. Multiply this times this, I get minus y sine xy. And I just leave this the same because I'm not doing anything here. Now, all the terms with dy dx, I'm going to want on one side, and the terms without dy dx, I'm going to want on the other side. Okay. So what I'm going to do is I'm going to move this 3 dy dx on the left side, and I'm going to move this negative y sine xy to the right side. So I want everything with dy dx on one side. So this is going to be minus 3 dy dx minus x sine xy dy dx. So all my dy dx terms are on the left side, and all of the terms without a dy dx are on the other side. So I am going to have a 1 plus y sine xy. I factor out a dy dx, and I get -3 minus x sine xy is equal to 1 plus y sine xy. And then I'm just going to divide both sides by -3 minus x sine xy to get the dy dx by itself. So my final answer here is this. So all you're really doing here is following all of the differentiation rules you know. Product, quotient, chain. But anytime you see a y, you have to put the dy dx term here. Okay, let's do this one. Ln x times y is equal to sine x. Before we even do this, there's actually a couple of ways we could do this. But what I suggest for you to do here is to actually use our logarithm laws. And if I'm taking a log of a product, I could just separate this into ln x plus ln y. Remember that? If I'm taking the logarithm of a product, I could separate this out. So I didn't take any derivative here. I just rewrote that as ln x plus ln y. Now, I just take the derivative of everything here. The derivative of ln x is 1 over x. The derivative of ln y is 1 over y. But since this term has a y in it, I have to put dy over dx. And the derivative of sine x is cosine x. Any term that does not have a dy dx, I'll move to the other side. So I have 1 over y dy over dx is equal to cosine x minus 1 over x. And then I'm just going to multiply both sides by y. And so dy over dx is equal to y times cosine x minus 1 over x. By the way, you don't necessarily have to start it by doing this. You could just do this. You don't really have to write this down, but I want you to pay attention that if you don't see that you could break it up by logs, you could just do 1 over xy, and then you have to do the chain rule with the product here, which is first times the derivative of the second plus the second times the derivative of the first, which is just 1 because the derivative of x is 1, is equal to cosine x. And there's really not space to do the problem there. But what ends up happening is you distribute this in here, and you get 1 over y dy dx plus 1 over x is equal to cosine x. And that's the same thing that we have here. And you would just subtract the 1 over x to the other side. So you could do it either way. You could separate it out by doing the logarithms. If you do not see that, and a lot of people don't see that, it works perfectly well with the chain rule. 1 over xy, but then because this is not just an x, you have to chain it. And the chain is a product rule, and you end up getting the same thing. Now, let's go ahead and look at example number 7. Given x squared minus xy plus y squared is equal to 7, find the equation of the tangent line and find the equation of the normal line. Okay. So this picture is just showing you what the graph looks like. But most of the time you're not going to have a graph to show you what it looks like, because you could just sketch the line here and do it, but we're not sure that you'll be as accurate as you probably can be. So the best thing to do is just to take the derivative. So if I take the derivative, this is 2x. I have x times y, so I have to use the product rule. First times the derivative of the second. The derivative of y is dy dx plus the second times the derivative of the first. The derivative of negative x is -1. Then I take the derivative of y squared, that's 2y dy over dx, and the derivative of 7 is 0. Okay? So we just do our normal solving here. Anything without a dy dx term will go on the right side, and I'm going to factor out a dy dx here. Okay, what I'm going to do is I'm going to switch it, because usually they like putting the positive term first. They don't like putting -x plus 2y on any type of test for multiple choice. So I'm going to write here that this is 2y minus x. And then if I bring this to the other side, this is -y. So if I bring this to the right side, it's positive y. And this is positive 2x. So if I bring this to the right side, it is minus 2x. So once again, I just factor out a dy dx, and I'm left with 2y minus x. There is really nothing wrong with putting minus x plus 2y. I won't mark you off for that. But I'm just showing you that most problems, like if it's a multiple choice, they'll usually want to put the positive term first. Okay, so now if I was solving for dy dx, I just divide by 2y minus x. So this is the derivative. But I want to find the value at -1, 2. So let's go ahead and do the math here. If I want to find dy dx at -1, 2, then that is equal to, I just plug it in here, plug in -1 for x, 2 for y. So this is 2 minus 2 times -1 all over 2 times 2 minus -1. And so this is 2 plus 2 over 4 plus 1. And I get that this is 4/5. So I could write the equation of my line. They already give me my point. So look, here, I don't even need to plug it into here. They already give me my x and my y that I'm going to use for point slope form. It has to go through the point -1, 2. So the equation for the tangent line is y minus 2 is equal to, my slope is 4/5 x plus 1. And then remember, the normal line is really easy. The normal line is just always going to be the opposite reciprocal of the tangent line. So this is going to be y minus 2 is equal to negative 5/4 x plus 1. Now the next thing we are going to talk about is to talk about second derivatives doing implicit differentiation. So what we're going to do now is we want to find the second derivative of this function, y squared minus x squared is equal to 4. Okay. So we're going to go ahead and take the derivative like we normally would for y squared minus x squared is equal to 4. So this is going to be 2y dy over dx minus 2x is equal to 0. Of course, I'm going to bring my 2x to the other side. And so I get 2y dy over dx is equal to 2x. And I divide both sides by 2y. And so dy over dx is equal to x over y. So this is my first derivative. Okay. Now, what I am going to do is I'm going to take the second derivative. So if this is the first derivative, I'm going to take the derivative of this. Right? That's just like how you do a normal second derivative. So how do I do that? Well, now I'm going to do the the quotient rule. So this is the notation for this. So the second derivative, which is d squared y over dx squared, is equal to this. The bottom times derivative of the top. So it's y times the derivative of x is just 1, minus the top times the derivative of y, minus top times the derivative of the bottom, which is the derivative of y, is dy over dx, all over the bottom squared, y squared. However, I already know what dy over dx is. It's right here. It's equal to x over y. So I'm just going to go ahead and plug that into my second derivative equation. So this is equal to y minus x times x over y is just going to be x squared over y squared. So what did I do here? What I did is I substituted x over y into dy over dx. Okay, x times xy is x squared over y. Now we're just going to clean this up a bit. You'll never see answers that have fractions within fractions, the complex fractions. So my lowest common denominator here is y. I'm going to multiply both the top and bottom by y. And what happens is I get on the top y squared minus x squared all over y to the third. So what did I do here? Y times y is y squared. If I multiply x squared over y times y, the y's cancel out, and I'm just left with x squared. And look at the very, very beginning. Y squared minus x squared is equal to 4. So that means that I could substitute the top for 4. And this is my second derivative. Now, there are times where if you don't do it exactly in a certain method, you might not be able to plug in the original, which is fine, okay? But on a test, what might happen is they usually will, if they do have the original function here, and it's equal to something you get in your derivative, they'll always substitute this back in. And this only really works for second derivatives when you're doing implicit differentiation. We'll do it again. I'll show you how it works again for example number 9. So let's go ahead and take the derivative here for example number 9. So once again, this is an implicit because there's a y and an x. We're not really going to solve for y here. So the derivative of cosine y is negative sine y. But since this is a y term, dy over dx, and the derivative of x is 1. So this is pretty simple. I'm just going to divide both sides by negative sine y. And so dy over dx is equal to negative 1 over sine y. We usually put the negative on top. Okay. Okay, so once again, we have this. So we have to take the second derivative here. Bottom times the derivative of the top is 0, minus the top, so the top is negative 1, times the derivative of the bottom, which is cosine y. But since it's a y term, I need to put dy dx all over the bottom squared, which is sine y squared. Okay, so let's clean this up a bit. This goes away. Negative, negative becomes positive. And I know dy over dx is just negative 1 over sine y. Okay. So the top will become, so negative times negative is positive. So I'll have cosine y times negative 1 over sine y all over sine y squared. Now, if I have cosine y times negative 1 over sine y, what's basically happening is, okay, what's happening here is this is really cosine y, negative cosine y over sine y to the third. Because if I'm multiplying cosine y times negative 1 over sine y, I'm really doing this, right? This is the same as cosine y over sine y squared times negative 1 over sine y. And so this is why I get this. So what do I know cosine y is equal to? Go back to the very beginning. It's equal to x. So I know my second derivative is negative x over sine cubed y. And now We were having the 3 on the outside just to make it easier to see what we're dealing with, but in the end, you'll see the 3 back in there. Okay, last problem. Find the points at which the graph of x squared plus xy plus y squared equals 27 has either a horizontal or vertical tangent line. Okay, so we want tangent lines, so obviously we're going to take the derivative. So let's go ahead and take the derivative of this. So this is going to be 2x, the derivative of xy, so it's first times the derivative of the second, so it's x times the derivative of y is dy over dx, plus the second, which is y, times the derivative of the first. The derivative of x is just 1, so I'm left with just y. The derivative of 2y squared is 2y dy dx, and the derivative of 27 is 0. So once again, anything without a dy dx term is going to go to the right side. I'm going to factor out the dy dx here with these two terms, and I'm left with x plus 2y. And then if I divide both sides by x plus 2y, I end up getting this. Okay, now this is where you're going to use your knowledge of what a horizontal and a vertical tangent line is. So this is my equation for the tangent line. Or sorry, this is the equation for the slope of a tangent line. This is not the equation of a tangent line, obviously. This is the equation for the slope of a tangent line. And remember, a horizontal tangent, I'm going to abbreviate this as horizontal tangent line. The slope is 0, whereas a vertical tangent line, the slope is undefined. So if I have this as my equation for the slope, the horizontal tangent line when the slope is 0, so that's when the top is 0, right? If the top is equal to 0, then my slope is 0. However, to find the vertical tangent line, the bottom is going to equal to 0. Because the bottom, if the bottom is 0, then I have an undefined slope. So, and I'll have a vertical tangent line. So to find where my horizontal tangent line is, what I'm going to do is I'm going to put the top equal to 0. So I end up with negative 2x minus y is equal to 0. And of course, I'm just going to solve for y here. And so I get y is equal to negative 2x. Okay, let's just leave that here for now. And let's move on to the vertical tangent line. So I need to make the bottom equal to 0. So I move the x to the other side, divide both sides by 2, and I get y is equal to negative 1/2 x. Okay. So I still don't know the points though at where they have a horizontal or vertical tangent line. I just know that this is the relationship between y and x. So how do I find what the actual points are? Well, what I'm going to do is I need to get this equation here in terms of one variable. So what I'm going to do is I'm going to substitute negative 2x into y here, and I'm going to solve for x. So this is going to be x squared plus x times negative 2x plus negative 2x squared is equal to 27. Okay, let's do the math here. This is x squared minus 2x squared plus 4x squared, because negative 2 times negative 2 is positive 4, is equal to 27. X1 minus 2 is negative 1. Negative 1 plus 4 is 3. So I have 3x squared is equal to 27. X squared is equal to 9. And so x is equal to plus or minus 3. So I know my x values, and then I'm just going to plug them into the y here to find my y values. So if x is negative 3, negative 3 times negative 2 is positive 6. And then if I plug in positive 3, negative 2 times 3 is negative 6. So this is where I have a horizontal tangent line. And you can see on this graph at negative 3, 6, it kind of flattens out here. And at 3, negative 6, there's a horizontal tangent line there. Okay. So we're going to do it again for the vertical tangent line. I know y is equal to negative 1/2 x. I'm going to plug it back into that initial equation. So I have x squared plus x times negative 1/2 x plus negative 1/2 x squared is equal to 27. This becomes x squared minus 1/2 x squared plus 1/4 x squared is equal to 27. Okay, if I combine these, this is 1 minus 1/2. So I have 1/2. 1/2 plus 1/4 is 3/4 x squared. Because remember, 1/2 is really 2/4. So 2/4 plus 1/4 is 3/4 is equal to 27. Remember to solve for the variable. If I multiply by a fraction, I just multiply by its reciprocal. So this is 9. 9 times 4 is 36. And so x is equal to plus or minus 6. And once again, we can just plug them into this relationship here that y is equal to negative 1/2 x to find my points. So one of my points has a negative 6, and one of my points has a 6. Negative 6 times negative 1/2 is positive 3. And positive 6 times negative 1/2 is negative 3. So this is my vertical tangent line. So obviously this was a lot. I mean, I don't think you'll ever see something like this on a test, but you might see to find where the horizontal tangent line is. And you should be able to do the left side. I don't think you'll ever see something where you have to find both the horizontal and the vertical, but that's how you do these problems. So that was a lot of information, and I know the method is kind of like a little weird to get familiar with because of this dy dx thing that we're doing, but hopefully when we practice in class, you'll be getting the hang of this.